Well, good morning or good afternoon, depending on what part of the country you're at. This is Chris Kopak, Assistant Vice President of Facilities Management at the University of Arizona, and also current APA President. This is our continuation of our monthly webinar series. These have been very successful, and listening to our members, they said, could we try to do one at the Eastern time, catch the noon time? And looking at that, we're going to have over 700 attendees on this call. So we want to make sure we're reaching from the Pacific to the Atlantic, so this is working out very well. Today we have a topic that affects a number of us at our universities, research labs and being as efficient as possible. Smart Labs Roadmap to High Performance Laboratories. We have the pleasure of Thomas Smith, President of Exposure Controls Technology. Thomas has spoken at some of our APA conferences in the past, most recently in Nashville. Also, Hoy Bohannon, who is the President of Hoy Bohannon Engineering. And so, gentlemen, we appreciate you taking time out of your busy day to give back to our members. It's really one of the goals we have with APA is, number one, our strategic effort was giving back to our members so they have something useful. So it's a 45-minute presentation. And as always, we'll be taking questions the last 10, 15 minutes. Feel free to go ahead and type those in. And just so the flow goes smoothly, we'll hold the questions to the end, but do go ahead and type them in, and then we'll be addressing questions for the last 10, 15 minutes. So with that said, Thomas and Hoy, thank you again. Take it away.
Thank you, Chris. This is Hoy Bohannon. I'm an engineer with a lot of experience in buildings. So my background basically is air quality and buildings. So as you can see, I've been a facility engineer, facility manager, and lately have really worked on consulting with air quality issues and air movement issues in buildings. So my perspective really is going to be from a facilities perspective, talking about the introduction of labs and smart labs and the challenges that we have in facilities. So if we look at the challenge of research is very serious work. And so many universities have research laboratories and research programs. These are very high profile things that can really make or break the reputation of the university. And for the universities that aren't research universities, you also have laboratories that are teaching labs. There's a lot of things in common between the labs and the way the labs operate and the opportunities that we have in labs. So if we look at labs themselves, labs are specifically designed to promote safe and controlled environments and that promotes science. And so if looking at labs, we know that labs also have hazards. They have chemical, biological, radiological, physical hazards, maybe only one, maybe all four of them in the same facility and location. So as a facilities engineer and facilities manager in dealing with labs, the question always was, well, what's going on in the lab and what are the issues? Well, the issue was that, of course, there's a lot of air. There's a lot of air moving through the lab, and the purpose of that ventilation system was to protect people and provide appropriate air quality. So we have airborne hazards. We have usually lab hoods or other source capture devices. And then there's air that comes in to dilute and remove contaminants, deal with spills. And then secondarily, we also want to control temperature and humidity. Temperature and humidity are very important in a lot of experimental situations. And the question that I had as a facilities manager was, well, what is all this about? And the answer always was, well, it has to do with safety and risk. So I talked to the industrial hygienist or the person that's in charge for the safety of the lab, and they said, well, it's about safety. And we can't really change anything because it would change the safety in the lab. And that's kind of where we were. And again, that facilities experience was back in the 80s and early 90s. We were stuck. It was like, well, this is the way it is, and this is the way it has to be. So as we try and look at the risk in labs, and certainly we recognize there are risks, The labs are expensive and complicated. So in trying to manage those, you'll see that, an average lab size, especially for new lab buildings, is going to be 100,000 square feet, a pretty good-sized building. In terms of what it costs, it's up to $100 million in terms of what you'd expect to pay for a laboratory these days in a modern system. Your energy cost is also going to be high. So if you're thinking about energy or managing energy on the campus, and I'm sure all of you are, and you start to look at where's my energy going, well, if you have big labs, a lot of your energy is going into the big labs. So how do you manage that energy? How do you deal with the labs? Especially in thinking about in the past context, well, everything's about safety. We really can't change anything. So I would submit then, if we look at what's going on in the laboratories, a big part of the energy goes into heating, cooling, and ventilation. In fact, 45% to 80%, 85% of the energy consumed by fume hoods and the lab HVAC systems. So that's where the energy is. So if we look at our campus and say, well, the energy is going into the labs, and then we say, well, but the labs are using it because of these complicated HVAC systems, but we have this dilemma of we have this safety issue. So what can we do? And we look at the labs and the hoods; they're expensive, right? The fume hood is $25,000 to $50,000 each. So you're going to put in another hood. You know what the costs are with that. It's complicated. You've got to tie it in. And then we look at the annual cost. Just the energy cost is $2,500 to $5,000 a year, notwithstanding the testing cost and the other maintenance costs that go along with the hoods. If we look at that one hood, the hood probably is using as much energy as 3 houses. One of the things that we want to talk about and submit here as an issue is that as much as 50% of that energy is wasted by excess airflow, inefficient fume hoods, and improper modulation. Well, wait a minute. We just said we can't change anything because of the safety, and we're stuck in this box. And now there's somebody saying, well, there's some waste in there. We need to figure out how to identify that. And that's what we want to talk about today is how do we look at our systems and how do we put them together? So let's start with what's the purpose of the lab. The purpose is good science, right? Good science can happen in a bad building, but a bad building can affect good science. This is a quote from a researcher that has some major research projects at a university. From a research scientist. Well, I can overcome a lot of things, but if there's something bad in the building, I may not be able to overcome that and make my research come out well. So what do we have in buildings that have problems? We have poor control of environmental conditions. Sometimes it shows up as temperature. Sometimes it just shows up as variation, noise, and diffusers and so forth. And sometimes those really fail to meet the occupant's needs. When that happens, there's an issue with recruitment, loss of talent, and then inefficiency and costly to operate. We've already talked about the energy costs in labs, but there are other costs in labs. They're not your inexpensive building to keep up and maintain because of all the other gases and other things that are in the building and those systems. There is an increased risk in labs, and if things start to fail, then you have a greater potential for liability. And if you're in a situation that has deferred maintenance, and Chris referred to that as you've already had a presentation on deferred maintenance, it's a big issue. And it's not just in universities, it's an issue everywhere. Deferred maintenance can be significant. You say, well, you don't have to spend the money this year, just put it off, put it off, put it off. You have problems then of failure of critical HVAC systems, really an issue in terms of labs and lab performance. And so the question is, well, how did we get into this box? Why is this waste? Why are you saying there could be 50% waste? Well, there could be. Maybe it's not that much, but there's usually some things that can be tuned up. Well, why is that? And then how did it happen? Well, the first thing is the misunderstanding of risk and risk aversion. So again, back in the last century, back in the 1980s and 90s, when I was a facility manager, it pretty well stopped me just saying, well, it's safety. You can't change anything. It's safety. Well, there is a risk and there is risk aversion, but all labs aren't the same. And figuring out what those risks are and managing those risks are really the challenges. And so what's a system to manage the risk? What's the process for managing the risk? And that's really what we want to talk about in Smart Labs, which is a process. So most of the things we're doing in the future are going to be processes that we're going to manage, not rules of thumb. If we look at the old designs, especially the labs that were designed in the 80s and some of them in the 1990s, they're just based on rules of thumb. Here's the way all labs are. We're going to do it this way because this is the way we've always done it. Then as we got into the 2000s, we said, well, we've got these systems that can optimize things, and so they become more complex. And so if we get these very complex systems, variable air volume hoods and tracking mechanisms that track supply and exhaust, that becomes very complicated in terms of controls. And what personally I've found in some of the labs that have these advanced controls is you find that they're running at maximum capacity. You ask a question, why is this? Well, that's the way the engineer designed it. Well, the engineer designed a capacity, but it doesn't have to be maximum. You might be able to use the controls to tune it back a little bit. Right? That's a possibility, but often the systems are so complex that it's not really understood how to tune it and on what basis you tune it. And that leads to the next point, which is lack of training and resources. So in these really complex systems, if we have not good training or understanding by the operators of how these systems are supposed to work, then you end up with things that all run in maximum capacity. My experience is, again, as a facility manager, when things don't work and you get called in the middle of the night, there is a position called hand on almost every piece of equipment, and that's where it goes, because that's absolutely what you have to do is deal with the crisis. And so you're running from crisis to crisis to crisis, and the total management of complex systems and tuning things out really aren't the kinds of things that get done and handled in your typical facilities management role. Failure to manage change then, coupled with run to failure. Again, specific examples I know of and see often, you have a pump and a backup pump. You run them both, right? When one of them breaks, then there's still a pump running, and you fix the pump that broke, and you don't manage in terms of energy turning one on and off. You just keep them both on, running in hand, and that way you don't get calls at 2 in the morning, and frankly, nobody wants a call at 2 in the morning. However, with better systems, there are better ways to do that. The next issue really has to do with standard practices to achieve and manage performance. So what is the practice that you have in managing modern laboratories? The old rules were pretty simple. All labs require 12 air changes per hour. Well, that's a lot of air that you're moving through the labs. The next part, the corollary to that old rule is more airflow is better and safer. So if you cut it down from 12, somehow you've introduced these risks that we really don't know how to quantify, and we're not sure that it's really safer to reduce it off of 12 air changes. The follow-up to that from the old rules, the practices of the last century was all hoods require the same face velocity. They really don't. Hoods are not the same in this century as they were in the last century. And so that velocity rule that was the safety rule of thumb for the 1980s and 90s don't really apply here in the 2010s going into the 2020s. Airflow quantity is more important than airflow distribution. This goes back to more airflow is better and safer, and all labs require air changes of 12 or more. That's really not true. What's really is true, and what we know from modern research and the most recent research, is that airflow distribution is really critical and vital. Other rule of thumb, lab exhaust must be 3,000 feet per minute. And then the other thing in the old rule is that design, construction, and operations are separate activities. That really doesn't work. When the designer designs something, somebody builds something, and then you as a facilities manager and operator inherit this facility without instructions, without understanding what goes on, that leads to issues that affect your ability to operate efficiently and effectively. So the answer is that we can enhance the return on that investment. You've invested $100 million in this new facility. The facility is there to attract and retain top talent, we can improve the safety and reduce the risk. At the same time, it doesn't require more air. It requires managing the ventilation that you have. So ventilation management is really the key. The energy goes into the lab. Ventilation causes the energy use. So we can minimize the waste of the energy, maximize sustainability, improve resilience, mitigate deferred maintenance if we manage our ventilation systems, which leads to the roadmap to high-performance labs. And at this point, I'm going to turn it over to Tom, who's going to explain the roadmap and the process.
Thank you, Hoy, and I want to also say thanks to Renee and Chris for the opportunity to speak with you today, and thanks for everyone's attendance. We were very fortunate to have had an opportunity to work with the University of California, Irvine in development of their Smart Labs program. We learned a lot through that process. And I've been very fortunate in my career. I've started testing fume hoods as a stay-in-school student at the North Carolina State University in engineering, and worked for the federal government testing fume hoods until I started a company in 1994 to go out and help facilities evaluate their systems. And so I've been very fortunate to have had an opportunity to work with the AIHA, the American Industrial Hygiene Association, and ASHRAE, and currently serve on the board of directors for the International Institute for Sustainable Labs. So over the past 25 years, we've been working with facilities to better understand how to operate and manage laboratories. And I started the company to really test fume hoods, and we found a whole variety of issues associated with design and operation of laboratory hoods. I helped write the EPA standards for laboratory ventilation, and I was challenged by their energy manager, a fellow named Dan Amon, who said, "Tom, I think we can run these facilities more effectively and more efficiently, reduce the energy consumption, but provide a safer lab environment." And so he challenged us to develop a program that at the time we called the Lab Controls Optimization Project, and it was very effective, reduced the energy consumption on the campus by 45%. Some of those tools were then adapted and applied at UCI to develop their Smart Labs program, and my involvement there was to help with development of some additional programs, primarily through the Health and Safety Department, to assist in implementation of this program on their campus. And that was very successful and involved development of some new tools and technologies. And I served as chairman of the Z9 committee for ANSI AIHA, and so we felt that some of these tools could be incorporated into standards and guidelines so that others might receive benefits for some of these programs. And then most recently, through the International Institute for Sustainable Labs, and then a separate effort through the Department of Energy, was development of a Smart Labs program, and they're running currently a Smart Labs Accelerator, where they're looking for partners to join the program and continue the success of this process. So Smart Labs is really about a roadmap, and that it starts with the recognition that there is going to be issues and goals for your facility. Maybe their energy costs are too high, operating costs, deferred maintenance, or safety issues. And then going through a planning stage allows you to evaluate the buildings and determine which opportunities are best to start, following on with an assessment, more deep dive into the actual building systems themselves to develop a scope of work, and then a construction renovation project to implement those energy conservation measures or performance improvement measures. And then finally, once you've got a building that's operating efficiently, effectively, we can move on to the management phase, keeping it working properly. And together, those are all the tools and steps that would make a smart lab. So we can break those tools down into a very systematic approach that's comprised of a various series of phases and tasks. And so we have phase one is really about planning and assessment. Qualitative Scoping Study, that's intended to evaluate the buildings and determine opportunities and prioritize opportunities. And then you make a more significant study involving a quantitative performance audit. And from there, the outcome is a scope of work. That then leads to phase 2, which is construction, renovation, or an upgrade project of various different magnitudes. And then finally, the final phase is the ongoing life cycle management program. And so it's a very systematic, logical process that takes you through these steps. So we start first with our qualitative scoping study, and it's really to identify the best projects to start first. And so when we look at a campus that may have multiple buildings or a building that may be identified for optimization, there are some key performance indicators that enable us to classify that building, and we use a system of A, B, C, or a D. So based on the state of the systems, the current energy consumption, the likely complexity and of the project to implement, and the return on investment, we can classify buildings. And so sometimes your building may classify as a C or a D, indicating there may be lots of opportunities, but there also may be issues with the base infrastructure, the air handlers, the exhaust fans, the boilers, the chillers. Conversely, you may have a newer building or a more simpler building that might classify an A and a B that may have tremendous opportunities for energy reduction, but the investment is going to be considerably less. The time frame for execution is going to be less. And so we like to start with those buildings where we can build our team, gain success, and then utilize those benefits to approach the other buildings. So having gone through this first phase of evaluating and doing the qualitative study and optimizing, we now have a list of buildings, and we move to the second step, which is a more detailed evaluation, gathering the building design documents, a risk assessment, operational tests, development of specifications, the energy evaluation, and that's really part of the quantitative performance audit. And so much more detailed evaluation of the building. Let's take a look at a building, for example. As Hoy mentioned, the ventilation drives both safety and energy use. And so our perspective, I'm both an industrial hygienist as well as an engineer. So we look first at what happens in the labs. What kind of exposure control devices may exist in the lab? Are there fume hoods, ventilated enclosures, snorkels, specialty devices, biosafety cabinets? Those all may have ventilation requirements. And so we have to have that connected to an exhaust system, and then we have to have some way of distributing the flow through those systems, so some type of balancing dampers. We may have a combination of constant air volume systems that are single hood, single fan, or manifolded variable air volume systems with complex multiple N+1 type fan units. We also have to supply the air back to the building and ensure that it has proper distribution. So here we have two independent systems that are working together. So they're independent but not mutually exclusive because they both have to satisfy that objective of safe operation as well as proper indoor air quality for the space. Now we want to recover some energy, so we're adding a little more complexity to the system, and our building automation system can be added so that we can control and modulate flow and sense airflow and different operational parameters of the systems. So all of these parts and pieces are working together, and then we can add a demand-based control system based on occupancy or contaminant sensing. And so now we've got a pretty complex system. Now, they don't have to be complex in order to be optimized, and they don't have to look like this to be a smart lab, but they need to be operating together as efficiently and as effectively as possible. And when we do that, we bring our people in, and they begin using the labs, and we anticipate that there's going to be some modulation and flow based on their utilization and their demand. And we may start with some low flow when the lab's unoccupied, and then as people begin occupying and heat loads go up and start using the fume hoods, then we expect a range of modulation. Now that has to be matched by the air supply system in order to keep the proper air balance. And as Hoy mentioned, there's going to be some correlation to the energy consumption. So if we look at knowing what these minimum and maximum values are, we have some way of begin to understand how the system's operating and how to optimize the performance. And we can look at key metrics such as averages over days, weeks, months, or years, and that'll provide us some information and insight into the operation. Well, all of the different types of labs that might be encountered, from chemical labs, biology, nanotechnology labs, are new and areas that are really becoming important areas for research. Even the teaching labs could be put in here as special labs. And so all of these labs will have different risk associated with their potential for exposure. They'll have different functional requirements, and that's what defines the demand for ventilation. When we look at the demand for ventilation, we're going to use that to establish the design and operating requirements, based firstly off of safety. What's the requirements for the hoods? What's requirements for contaminant removal and dilution? Maybe there's a requirement for isolation and pressurization. Secondly, we can look at what are the comfort and productivity requirements. Some equipment may require tight operating tolerances and have specific requirements for the climatic conditions within the space. And then we can look at occupancy and utilization. And if we understand these parameters properly, we can look at what is that minimum flow and range of modulation that's necessary to meet the needs of the occupants. Because at the end of the day, this project and these buildings and these labs are meant for the research to be successful. So it requires a management program to really understand how to ensure the environment is helping the researchers be successful in whatever science they may be pursuing. So looking at their utilizations of labs, people don't work in the labs 24 hours. They may work in some labs 24 hours, but if you generally study the amount of time spent in the labs, the time away from the labs on nights and weekends and maybe holidays and leave time, if we start to look and plot actual occupancy and utilization, we generally determine that as much as 75% of the time the labs are unoccupied or not in use. And so that creates a great opportunity to reduce flow during periods of low activity, and that enables us to conserve energy. So looking at looks like we just had an interruption in our program. Apologize for that.
I know we'll get that. This is Chris. I know we'll get that just in 1 minute if you sit tight. We have a lot of questions that are coming in. There we go.
Okay, all right. Okay, so as we look at the change in flow through the systems, if we have an understanding of how this flow translates from minimum to maximum, then we can use that information to plot and trend that performance over time. And so knowing the minimum and maximum flow allows us to evaluate whether operation is within the expected boundary conditions. And then we can correlate that with metrics such as average flow that could be done daily, weekly, monthly, or annually. And that allows us to use those metrics to better manage the systems. When we look at that information and that correlation between flow and energy consumption, it allows us to utilize those metrics to understand how does demand affect operation and then subsequently energy consumption. So our energy can be measured in a simple metric, maybe dollars per square foot, airflow in terms of the CFM per square foot for the building, and then the efficiency in dollars per CFM. So when we look at reducing the total energy consumption by reducing the total airflow volume, we can reduce the CFM per square foot. But if we make the system more efficient, we can use less cost to heat and cool and transport the air through the building, thus reducing the cost per CFM. So that's the combination of those two factors that we really want to focus our efforts. But looking at a laboratory layout, looking at the floor plan, we have to decide what airflow goes where and when is it going to be necessary. So looking at a floor plan, we may lay the systems over top of that floor plan and evaluate, is it adequately distributed? Can it be controlled properly? What are the proper flow requirements? And so we say, how much flow is required? Where is the flow required? And then when will it be required? And what kind of modifications can be implemented to ensure that we better control flow and modulate as necessary? Our first look at the floor plan is where's the risk? What flow is going to be required? So we can look at this lab fairly generically, and we would say, well, sometimes there's the application of a prescriptive air change rate that might apply to the labs. But if we look at this particular building, the labs are in the middle. We got support spaces around the exterior and then offices. And so we want to know the flow cascade and then identify the areas of primary concern. But as we know, the risk in the different labs may be range from negligible to extreme. And just like we have protective devices, such as canopy hoods to snorkel devices and fume hoods and glove box isolators, each of those are going to be appropriate for different levels of risk. And then secondarily, the lab itself may be needed for secondary containment, so switching between air change rates. And as that level of risk goes up, so too may be the need for more airflow or more quality of the airflow. So at the University of California, Irvine, they were very interested in applying this type of program, but making sure they had the right flow at the right place. And so we developed a risk assessment, which allowed us to evaluate the labs based on the potential for exposure to airborne hazards. So this categorized labs like from 0 to 5, where 0 would be a negligible lab. Maybe it's a computer lab where there's no real chemicals being used. Conversely, you may have an extreme hazard lab where they're working with chemical warfare agents. And so this differential in the type of risk can be associated to an airborne emission scenario based on exposure or control limits, quantities of materials, potential for generation, what's the resultant concentration profile. From there, we can use a scorecarding approach where we identify the risk factors and we evaluate the lab, starting with negligible. There's really no hazards associated with this space, till we move to the lower scale of an extreme environment. There may be multiple hazards used in large quantities and various different procedures, and based on the scorecarding approach, it may add up to an extreme risk lab. So taking these values and looking at each lab independently, we can rate the risk factors and then weight those to come up with an overall scorecard, and then allow that score then to be compared to an appropriate operating scenario and then a operating specification. From that, we can look at the distribution of risk within the spaces, and you can see that in this particular distribution, 35% are in the category 4, so a prescriptive air change rate may not be appropriate for all of the labs within this space unless you were going to guarantee it for the most hazardous space, in which case it may be excessive for many of the other spaces. So we can then also apply that rating back to the floor plan, and now we can identify where these areas of high concern are located. And that may then drive the specifications for airflow. It may also drive the design of the systems, and it may drive the need for inspections and routine preventative maintenance and other factors, so that we are identifying where the important areas are and where to set the criticality for various efforts. If we look at this distribution, we've had an opportunity to perform this investigation in many different buildings of many different organizations, and we can see that the distribution varies widely. The chemistry labs, as you might anticipate, have a higher proportion of risk in their lab spaces. And then we have, say, an energy lab where they're not doing a lot of chemistry type work, and so the airborne hazards are lower, and so we could operate at a lower flow and potentially with less energy consumption in these type of spaces. But we have to understand that risk profile. So once understanding the airflow specifications and the risk profile, we develop a scope of work during the phase 2, which leads us to all kinds of different opportunities to improve performance and conserve energy. We can remove and hibernate unnecessary hoods. We can upgrade traditional fume hoods. We can replace fume hoods with high-performance hoods, upgrade the airflow control systems, reduce or reset system static pressures, optimize air handlers and exhaust fans, implement energy recovery. These are all possible opportunities, but may not all be applied, and there could be many factors that make them more or less appropriate for the space. Budgets, time constraints, the system status, and so forth. So all of these factors have to be investigated for the appropriate scope of work. One of the things that over the years we've been able to understand is based on our analysis of risk, we've been able to develop some new technologies and work with manufacturers to deploy new technologies and new methods that have resulted in safer and more efficient labs. For example, we know that we can upgrade traditional hoods by installing new high performance components that make them contain better at lower flow. The VAV controls, the manufacturers have done a great job at upgrading the controllability, and the sensitivity and accuracy of these controls has improved, the feedback mechanisms, the installation of demand control ventilation, either through sampling of air contaminants or by looking at occupancy and utilization of the space, can enable the modulation of flow. And then most recently, we've been working with diffusers to provide better airflow management within the space. Try not to focus on the quantity of air, but the quality and how air is distributed through the space, as Hoy was mentioning earlier. These tools together can often lead to a 40% reduction in flow, which translates to a very significant energy reduction. These techniques were employed at the University of California, Irvine. It's a picture of their campus. And so when we looked at the buildings that they deployed these types of programs, they ended up with a 58% energy reduction. And so very significant savings, very successful program on their campus. And so, but there was some discovery, and one of them was that even well-designed and well-maintained buildings, they can degrade over time. These are mechanical systems that are subject to wear, and there is the potential for change in how they're used and operated. So success requires a combination of efforts. It requires the right design and mechanical attributes, as well as leadership and management. And it's together through this program of the Lab Ventilation Management Plan or Lab Ventilation Management Program that these components can be brought together to achieve the success of a safe and energy efficient building. The roadmap helps to describe those steps and tasks of the process to give you a path. And it finalizes with the phase 3, which is the management component. So we want to manage that system so that we can modulate the airflow to meet the needs of the users. And if we achieve that modulation properly, then it'll be both safe and efficient. And so the management program has some fundamental basis. First of all, we have to understand the risk, the demand for ventilation, and the airflow specs. From there, we have to ensure that we have the right type of laboratory hoods and the airflow control systems are capable of meeting the needs of the occupants. Thirdly, we want to make sure that we've got the right building information, the dashboards and the analytics, so that we can evaluate operation and understand how the building's performing at all times. And then finally, we want to make sure that all of the key stakeholders are involved in the management and ongoing operation of the building to keep this building a safe and properly operating lab environment. So leadership is the key to the program. At the University of California, Irvine, Wendell Brazzi is the Associate Vice Chancellor, and he coordinated his team, Matt Gudorf with Energy and Mark Gomez from Safety and various other folks came from different departments, and they worked together as a team. But not only did they work internally, they also involved some specialists from exterior, those contracts and vendors, to apply their skills and techniques and formed a team. And from that could be coordinated and managed to implement within the buildings themselves. One of the things that's often interesting is when we were working with General Motors and upgrading some of their labs, there was the recognition that your vehicle comes with an operator's manual. And if you follow the instructions in the operator's manual, change the oil, check the tire pressure, do the recommended maintenance, that car will stay on the road for a long period of time. However, your buildings don't come with these operator's manuals. And so we've got to fix that process between design, construction, and ongoing operations where some of the deliverables are in fact these operational manuals that help maintain the building. And it has to be coupled with training so that we understand how these more complex systems, what are the tools and right procedures to keep them working. So some of the items that we need as part of this program would include up-to-date drawings, system line diagrams, airflow specifications, procedures, key performance indicators, and training being a major component of the program. And if we do that properly, we're going to protect that return on investment. And oftentimes the reputation of the organization is based on the success of the research. And so we want to make sure that the building is a tool for the users to be successful, and that tool helps them achieve their end objectives. Smart Labs recognizes that there's a need for training for all of the stakeholders involved, from the program managers and supervisors of the different departments to the practitioners and the people working in the buildings themselves. All need to be equipped with the appropriate knowledge and tools and training so that they can be effective and work as a team. And recently we've developed a ventilation management program coordinator role that can be trained to effectively integrate these operations and serve as a liaison between departments. It's really a key role, and it can come from within the organization itself, or it can be contracted or hired as a person to help and assist through this process. So the roadmap really helps to accelerate this process of implementation. Starting with the planning phase, you look at your multiple buildings, you do an assessment to evaluate and identify what areas are prioritized. Then you can select those buildings for a deeper assessment. That's where you get into your energy evaluation, systems evaluation, the risk assessment, scope of work, and from there move to the optimization phase. And there's some time frame that's going to take. And the more effective your organization is between coordinating these resources and the better program that's in place, the quicker that process can be undertaken. But we've seen projects take anywhere from 1 to 3 years to complete a building. When that building is complete, then it has to be managed so that we don't lose those savings. And while that goes on, these programs can be implemented either sequentially or concurrently in other buildings so that you achieve these objectives on the campus. And so it really becomes important to have the appropriate management program in place to plan and optimize the buildings to minimize the time frame and cost and provide predictable results. So these new methods are being deployed in numerous different organizations. We're working with the government labs and industrial labs and universities and pharmaceutical companies to deploy these methods. And we're seeing very similar results in all of the different organizations. To some degree, these programs have implemented fully, and in others, they're just being initiated. There is a program that the Better Buildings Alliance through the Department of Energy has started as a Smart Labs Accelerator program, and it's based on this Smart Labs program for UC Irvine, and you can become a partner. And some of the partners, there's a growing list of Accelerator partners today, UCI, University of Illinois, University of Minnesota, to some of the government labs. And so there's a website address here. If you just type in Smart Labs Accelerator into your search engine, you'll be able to get some more information on the Smart Labs program itself. That program provides some additional resources, references, training, and other services, even some consultative support through the program. And most recently, we've published a guide called the Roadmap to High Performance Laboratories. It basically explains how to implement the program, strategic planning, to build the team, talks about systems theory, and then the phases of implementation resulting in an airflow management program. So if you're interested, you can contact us and we can make it available through APA so that you have that as a reference source. Again, it's a very high-level guide providing the basic of what to do if you want to try and implement this type of program. So our basic philosophy is at Exposure Control Technologies is the right flow in the right place at the right time. And we believe that if you look at the systems, you understand what the flow requirements are, you can manage and maintain these systems and keep them operating efficiently and effectively basically forever. And that will help to not only reduce operational costs, reduce energy consumption, but it'll also limit and reduce that deferred maintenance, which has become such a great problem for so many facilities. So at that point, we can stop. I want to acknowledge Hoy. Thank you for being a part of the presentation today, and APA, thank you for your provision of the webinar, and then all the folks at UCI and DOE and I2SL. So at this point, we can open up for questions.
Well, Thomas and Hoy, thank you very much. And this is definitely a topic that is of interest based on the number of questions. And Thomas, you mentioned one of the big challenges is the deferred maintenance. And the fact is that a good 50% of our deferred maintenance is HVAC related. How is that being addressed when you have some pneumatics in buildings? As Mike Hoffman, one of the energy managers online, was talking that you have pneumatics and you have some of these older air handling systems.
Well, that's an excellent question. So when you do your initial assessment, you're going to evaluate those pneumatic systems, and some components are going to be more critical to the operations and the type of activities that are going on within the space. So identifying what is the level of modifications that are necessary, what's the end goal, and what you're trying to achieve determines the criticality of those modifications. Now, it may be that a simple conversion to constant volume could be a short-term solution. And in some places, recently we worked with an organization to develop a plan that would enable an organization to implement change over a multi-year cycle, say a 5-year plan. So within the budgets, they did the first year they implemented a certain part of the program. They might have upgraded the hoods. The next year they did the controls. The following year they did the building automation system, and then so forth. So over time, they used the budget and the budgetary constraints, and they implemented a longer-term program. So they didn't get the results immediately, but they were able to achieve those results by addressing them in a sequential fashion.
Thank you. Another question that came in is that you have a number of key stakeholders. Can either one of you talk a little further? It's not just the facility staff. You have the lab operators, and in a lot of cases, maybe it's the risk management staff. They're used to doing it a certain way. And when you're talking about reducing the volume of air coming in, there can be some pushback. How have you been able to get over those hurdles?
Well, yeah, this is Hoy. Absolutely, there's going to be pushback. It's a process, and again, the process is you need to start with those conversations. The pushback, it really does depend on the individuals and the groups you pull together. Most of the safety people are concerned about safety. That's their job. And the idea that, well, everything's always the same is that's the way they've always done it is a hard one to deal with. But I think it's as you present, we're trying to manage risk better. We're trying to manage sustainability. So it's a management process, and you talk about you don't approach everything the same way in terms of your approach to safety. You can start to work through those discussions, but it's certainly a place to start. You can't leave them out of the conversation to start with, or the program will go nowhere. So they've got to be involved at the beginning and have those conversations. And Tom has butted heads and converted a lot of people through talking through the process. So Tom?
Yeah, I'll just add to that each of these groups brings expertise to the overall operation of the building, and health and safety and facilities and controls and are all have specialized knowledge, and it's really working together that you can discuss some of the concerns, and where there's a need for additional information, you can look at references, you can conduct additional studies, and you can oftentimes overcome those concerns with the appropriate information, but it's got to be based fundamentally on risk mitigation and ensuring that you're meeting the needs of the occupants. And so that's really the overall objective.
Excellent. And really, it's the teamwork that you're talking about, and you emphasize that. Nicole Savage has an excellent follow-up question, and it's about that teamwork, that as you're reducing the amount of air changes from 12 and then reducing it down, you partner with the current lab occupants. what happens when those labs turn over and you have new researchers? How are you making sure that information is getting out to everybody?
That's a great question because, just like original design, if you start your original design, by the time you've got to construction, it's very likely that the occupants may have changed. And so some of those original design specifications may not be appropriate. So too as change occurs in the labs. Labs are dynamic by nature. There are new people coming into the labs. There are new processes and procedures. So part of the lab ventilation management program has to include a management of change process. And that management of change process can use various key triggers to identify significant change. Now, of course, you want to set up the controls and the specifications to be conservative so that you're not underestimating risk, but you don't want to grossly overestimate risk either. So finding a way to be conservative and then using trigger points such as space planning, the researchers themselves being trained on what's a significant change, bringing into play the fume hood testing program, the annual lab inspections. There are various key elements that can be incorporated into the management of change to identify when a significant change has occurred and when the system operation may have to change to accommodate that change.
Thank you. We have a question from Maureen Coltless, and she's asking about the data of labs being, you made a comment about labs being unoccupied roughly 75% of the time. Can you elaborate a little further on that, and where are you getting those metrics from?
Okay, absolutely happy to. Let me go find my slide that describes that topic, but essentially, there are certainly labs that will be available and need to be available 24 hours a day. And when we look at the information by trending the utilization, so in labs that we've had occupancy sensors, both on the hoods and in the lab itself, we're able to see what's going on in the lab. Are people using the lab? How often are they using the lab? So that's given us the ability to analyze some real data about utilization of lab space. Now, oftentimes, a researcher needs their lab available, and they'll go in and do some experimentation, and today's technology gives them the ability to collect a great deal of information that then needs to be analyzed and evaluated, and oftentimes that's not done in the lab space itself. So that can be looked at. Now, that doesn't mean all labs have this 75% of time when they're not being used. Some labs may operate 24 hours a day, and you have to accommodate that. But like I tell the folks that work for me, that when they ask about vacation time, I say you get 104 days off a year. They're called Saturdays and Sundays. So people do take time off, and there is vacation time, and sometimes the labs are unoccupied. And so the question becomes whether it makes sense to have a system that can modulate flow to take advantage of those periods of reduced activity, and are we incurring any additional risk when that does occur? And so we have to take that into account, evaluate that, and then make a thoughtful decision as to what is the appropriate investment.
And similar, I would say that often in teaching labs, you can figure that out. You walk by and look at the class schedule posted on the door, and you'll see there, it's not 8 hours during the day. It's Monday, Wednesday, and Friday from 1 to 4 or something like that. So that there's just not a lot of occupancy in some of those labs. That would be at one extreme. I mean, the other would be labs with a lot of researchers that are spending a lot of hours in the lab. But as Tom says, my observation also is that they set things up and they let experiments run in the hoods and they're monitored by other devices. So the occupied really means there's not somebody in the lab during those hours.
Thank you, guys. And just for everybody who's sending the questions, and we have so many questions, and we're run out of time. We've got about 7 minutes left. Feel free to keep sending the questions in. If we don't get to your question, we'll address that when we post everything. It'll be on the APA website in about a week, the PDF of the webinar, the PowerPoint, and the audio. Another question that's come up from Stephen Graves. can you discuss technologies and strategies to safely modulate the exhaust fans, exit velocity, and how this affects the ANSI Z9.5, which recommends exit velocity of 3,000 feet per minute?
Okay, that's another excellent question. So we clearly, as we are dealing with the exhaust of hazardous materials, if we have an understanding of the risk associated with the laboratory hoods and the labs that are being exhausted by a particular system, once we have an idea of the risk associated with the hoods and the lab environment, we can get an overall rating of the activity that might be processed through the system itself. And so when we look at that, we can evaluate what is the risk associated with the overall system and what's the maximum credible type of a contaminant load that might be in the duct. And then through evaluation of the exhaust fans, you can take a look at stack heights, increasing stack heights to compensate for for discharge velocity. There are induced air fans that have the ability to dilute and discharge in a more effective manner. There is the ability to apply computational fluid dynamics and wind-wake models, which we would recommend in all cases of new laboratory design, and in many refurbishment of labs as well, to evaluate what are the actual requirements to ensure the proper exhaust so that it's not affecting people working on the roof, it's not affecting people that may be working nearby or into the air intakes of the buildings, the building that we're working in or the building next door. So it's very important to not just apply the rule of thumb of 3,000 feet per minute and 10 feet above the roof. That may not guarantee it. It may need to be more in some cases. If you have a very high risk application, you may have to actually filter that exhaust before discharge. So it's important to start back down in the lab, look at the applications, use a bottom-up approach to evaluate the necessity and the importance of that exhaust. And then once you have converted that to an emission scenario, then you can run the models and do some evaluation of the appropriate design that would prevent re-entrainment or exposure to people working in, on, or around the building.
Yeah, as a follow-up on that, the idea of the high flume velocity is that you're doing a large-scale dispersion of whatever's in that plume, and so the dispersion model would be that somewhere, whenever that plume comes back to rest at the ground level, everything is at a very, very low concentration. As Tom said, sometimes that's not going to be enough. If you have a 2-story lab building next to a 10-story building, that dispersion is not going to do what you want. Again, the rule of thumb is that's kind of for a worst case, except when the tall building connected. So the worst case is under certain wind conditions and certain weather conditions, then you're going to be safe, which may only happen like 10 hours a year. The other 8,700 hours a year, you really don't have that condition where you really need 3,000 feet per minute. And so that's another consideration, especially if you have really high volumes. You may not need that. Again, it depends very much on the surroundings, what the buildings are around, what the weather conditions are, and the topography of where people would be and other things in the environment. So it's kind of the maximum thing. It's kind of like the 12 air changes. It's the most you would need most of the time, but not all the time. So I think that these days we have more advanced ways of looking at it than using those what were generally conservative rules of thumb.
Yep. So understand the risk and design appropriately.
Thank you. Can you guys hear me okay?
Yes.
Yes.
We're getting close to wrapping it up. We had more questions and we're going to have time. Is there any final thoughts? And Thomas, we'll go with you first. And again, we appreciate very much taking the time to share this. When you talk about roadmaps to high performance, when you're talking about energy efficiencies, reducing energy usage by 45 to 85%, all in a safe manner. You're talking to everybody on the line and then some about how we drive down our utility costs and still provide outstanding services to our colleges and universities. So again, thank you very much for your time. Thomas, any final thoughts?
Yeah, well, so there's been lots of lessons learned by organizations that have been undertaking this process and have resulted in successes and benefits for their organization. And we don't have to reinvent the wheel in many cases. Lots of this technology and these techniques are available, and there are tools that can be applied to reduce that learning curve and to make it more efficient and effective to implement these programs. And so I would encourage anyone to explore the DOE's Smart Labs Accelerator, to communicate with University of California, Irvine on their success, and to look at the resources that are available through ASHRAE, I2SL, APA, and the other organizations that are dealing and addressing these type of circumstances.
Thank you, Thomas. Hoy, any final thoughts?
Yeah, I would just say that you know, as you look around your facilities and your campuses, you have no two buildings that are alike. So if you're really going to optimize and manage both risks and opportunities in energy, you have to have different rules for the different buildings. And so this is a process for coming up with that. Like every other process that doesn't follow any specific rule, where you've got different rules for different places, then you have to manage it. So the commitment to management and the management of facilities means management of the ventilation systems, and that's really the key you need to take away. To manage the systems, you need to understand the risk, manage the risk, and then manage the systems and results.
Well, Thomas and Hoy, we're out of time, but again, I want to thank you both very much for all your help in presenting this to our APA members. Again, the presentation will be on our APA webpage. Usually it takes about a week to get posted. Renee Cota at the office here at the University of Arizona, we appreciate her help very much. And again, Thomas, Hoy, thank you. CEUs are available again. We will post all the questions that we couldn't get to also on the webpage of APA's webpage. And again, this has been part of my theme of harnessing and transferring the knowledge. There is so many excellent topics out there that we're trying to harness that information, especially as we're losing a lot of our key facilities officers due to retirements over the next 10 years. And so the more APA can give back, that's what we definitely want to do, useful information for our members. Next month, we plan on meeting and having a presentation on our Thought Leader series from 2017. Some folks did not get that information. It was transforming facilities to achieve student success, and that's ultimately why we all are here, is to graduate our students at our colleges and our universities. We'll have Nina Woolman presenting. We look forward to doing that on June 28th on a Thursday. Again, we'll be doing it at Eastern Time at at noon Eastern Time, 9 a.m. out on the West Coast. And again, Thomas, Hoy, thank you very much. We appreciate all your time presenting this excellent topic, Smart Labs Roadmap to High Performance Laboratories. Thank you, everybody, and we'll talk to you next month in June.
Thank you, everyone.
Thank you.